It's a pleasure to have Shaaban for the first time, Professor Shaaban Khalil, for the first time in our summer school and internship here. Prominent particle physicist in Egypt, especially, and director of the Center for Fundamental Physics in Kuwait City, and the founder of the center here. So we are grateful to him for that. There were already questions before about what is beyond the standard model for Professor Sayed, so he will hopefully answer some of them.
طيب خلصت؟ ده ستاندرد موديل كله؟ اقدر اكمل؟
كمل بقى بيوند.
اوكي.
ما كانش عايز يسيبك يعني. هو كان عايز.
تعالى اتفضل.
لو
عايز تكمل اتفضل. شغالين عربي انجليزي ولا انجليزي بس ولا عربي بس ولا؟ ها؟
هو انجليزي عشان اليكسير كمان.
Okay, so thank you for the invitation. Yeah, it's as Amr said, first time in the summer school because usually in July I will be outside Egypt, but this time I will start traveling after tomorrow, so I have the chance to give this 2 lectures only. If I stay more, I would give much more lectures, but anyway, also physics beyond the standard model for the student maybe still too early and too difficult, so I will try to be very simple and go to the conceptual points, not really technical issues. And anything you feel that it is difficult for you or you don't understand, stop me. We don't need to finish all the slides, we need just to give you a few things, but really understand. So I am Shaaban Khalil, as Amr said, ex-member of the CTB and now visiting, I can say visiting member. So I always be happy and pleased to come, although it's almost 1.5 or 2 hours from Zuwail to here. But anyway, the subject is, as I said, physics beyond the standard model, assuming that you had already introduction about standard model from Dr. Said Rashid, and I will have 2 lectures. So the first lecture now will be kind of trying to convince you that there is some evidence beyond the standard model or needs physics beyond the standard models. And in fact, I will also highlight the possible direction for this extensions of the standard model. Then after afternoon or after lunch, I will give you one example for very simple. Let us call it very simplest. A very simple example of the physics beyond the standard model. So this is general lecture about why beyond the standard model, what type of possible extension of standard model. This will be very close to the lectures of Dr. Rashid to complete these issues, and then next lecture will be an example of BSF. Okay? So now first lecture, evidence and possible direction beyond standard model. Again, I will just review make overview of the standard model. We already had it in the previous lecture and you remember, but maybe to set the notation and to set the points that I wanted to highlight here. So very brief overview of the standard model. Then I go for the questions that standard model cannot answer, what we call it evidence, especially if there is experimental evidence that is telling us that standard model cannot be the final theory, cannot be the underlying theory. It has to be an effective theory of much more fundamental theory. Then I go to discuss directions, what type of extension, what type of underlying theory the standard model could be an effective reference. Okay? So this lecture will have these 3 parts. Please, don't sleep. just be with me. Okay, so now standard model overview. I think now you know standard model SM. I think this is what you really learned now. We are abbreviated as SM. Is a quantum field theory. It's 4-dimensional quantum field theory, and based on the internal symmetry or gauge symmetry SU3 cross SU2 cross U1. SU3 for what? Which interaction for SU3? strong interactions. You forgot, you still lecture is so this is a gauge group which described strong interaction. SU2 supposed to be for the weak interaction, and U1 hypercharge contain the electromagnetism. So the standard model is really describes three types of interactions in our nature: electromagnetic, weak, and strong. How many interactions in nature? Four. What is the missing here? Gravity. So this is the first question, that standard model is not final because it doesn't include gravity. Okay. Now the particle content of the standard model is fermions and gauge bosons, and of course Higgs. So this is a standard model particle content that I am sure that you already have seen. So the standard model fermions, we have left-handed fermions, left-handed quarks, and left-handed charged leptons, and right-handed quarks and right-handed charged leptons, and also, in fact, left-handed neutrinos only. So now this is a way to write the left-handed in doublet, because SU2, you know SU2 is what? Unitary matrices 2 by 2 special, because S is determined to equal 1. So any fundamental representation of the matrices like Pauli matrices 2 by 2 sigma or tau is fundamental representation is a column or two components, a scalar or two component doublet like this. So this is the reason why under SU2 we have these doublets. So we constructed a matter field in doublets, as this is for left-handed only, to be charged under SU2 left. We will see, and you have seen already, the charges under the hypercharge and also SU3. Do you think if this is a doublet, because we are interested to show the particle content under SU2, under SU3, how it will be? The fundamental representation, the fermions, how we can write it if I wanted to write it under SU3. SU3 is similar to SU2, it's a unitary 3 by 3 matrix. So any fundamental representation will be triplet. So we need to have a triplet. Do you think triplet of SU3, do you know any example of triplet of SU3? You take only one quark, and the quark has 3 colors: green, red, blue, and this makes the triplet for each quark. Now the Lagrangian of the standard model may be too bit technical, but I will just tell you that you may be familiar with this term for the electromagnetic interactions or for the electromagnetic field. You remember 1/4 F mu nu F mu nu. This is the field stress tensor. This is a Lagrangian of electromagnetism. When you put it in the Euler-Lagrange equation, you get Maxwell's equation. So this is generalization. So this is similar to, in fact, this is U1, the hypercharge. This is for the SU2, because we have 3 generators. It's SU2, so we have 3 generators like Pauli matrices. So we have an index A, run 1, 2, 3, and this is for the strong interaction, which is SU3. So the joint is like Gell-Mann matrices 8. So the index here is running from 1 to 8. So anyway, this is what we call the kinetic terms for the fields, similar, as I told you, to the electromagnetic field. And then this is for the fermions, for the part. If you remember, or if you know how to write the term in the Lagrangian for Dirac field or your Schrödinger equation, you have a psi bar I gamma mu psi, for example. So this is a term, but each psi now represents either left-handed leptons or left-handed quarks or right-handed quarks, right-handed down quark, right-handed charged leptons. So we are separating them because we have what's called the covariant derivative, and the covariant derivative depends on the interaction. So left-handed quark has an interaction. It is quark, so it is interact strongly. It is left-handed, so it is interact under SU2, the weak interaction, and also it has a hybrid charge. So the covariant derivative, you change the normal derivative to the covariant derivative if you know this exercise in the electromagnetism by adding this generator times the field of the SU3, field of SU2, and this is the field of the U1 hybrid charge. So this is complete covariant derivative for left-handed quarks. For left-handed leptons, no strong interaction, so this term will not be there, but they left-handed, so they have SU2 and they have hybrid charges, so the covariant derivative will be like this, one term less than the quark covariant derivative for quark. Right-handed fermions, it is right-handed. Sorry, this is right-handed leptons, not fermion. Right-handed leptons has no strong interaction, has no weak interaction. Why it has no weak interaction? Because a weak interaction is left-handed. So anything left-handed will be involved in the weak interaction. Right-handed singlets is not interacting. For that reason, we don't have W here acting on FR or LR. In fact, I said this LR because if it is QR, we should have the gauge coupling of, or the gauge field of the strong interaction. So this is the way we construct the Lagrangian of the standard model. I usually say under SU2 we have this left-handed, you see neutrino left, electron left, and muon neutrino left, muon left, and so on. And the quark up and down. So this is the way we represent it left. While right, although we have U right and D right, but we don't have them in one doublet. We could construct them in one doublet like U, D, right as well. But unfortunately we didn't, or fortunately, we didn't do that because the leptons has only electron and the muon right and the tau right. No right-handed neutrino, because in the time of constructing the standard model, the neutrino was almost massless, not almost. It was at that time massless. So people try to avoid mass, and then they said we should not have right-handed neutrino to avoid the mass. And then the left-handed neutrino coupled with left-handed leptons and make this doublets. Right-handed leptons, right-handed electron, right-handed muon, right-handed tau. It doesn't find any right-handed neutrino partners, and they cannot construct this doublet on the right. Therefore, quarks also, because we wanted to build a theory where lepton quark similarity. So if the right-handed leptons are singlets, we were forced to keep right-handed quarks, although it is right up and right down, also singlets, and keep it scattered like this. Why I'm saying fortunately, because in fact if you constructed this and you make doublet like this, U, D, right, and imagine they said, okay, we can have right-handed neutrino and we kill the mass by some other mechanism, you could have also neutrino E, right, and everything will have a doublet left and a doublet right. This is more complicated model. It's called the left-right model, and this is one of the models we studied beyond the standard model, because now we discover that the neutrino will have a mass, or not will have, neutrino have a mass, neutrinos have a mass, and therefore we need right-handed neutrino, and once we have it, we can construct the right doublets, and then it takes us to what we call the left-right model. Left-right model is interesting. It has a symmetry between left and right. Neutrinos there, complete set of particle content. However, it's much more complicated. So it's fortunately that we started with this model, which is a standard model with a scattered right-handed sector like this, because it makes the model much simpler and much more predictive. And you see the model with this construction, which was kind of not complete, but very successful in fact. Look.
ايه الجاستيفيكيشن اللي قالوه ساعتها لما قالوا ان الليفت بس هو اللي له ماس؟ ايه الجاستيفيكيشن ساعتها؟
As I said, neutrino was massless, or was believed to be massless, and you know the mass of any fermions in the Lagrangian is coming from the interaction between left-handed and right-handed. If psi left, if psi right, usually we write in the, before left and right psi bar psi, m psi bar psi. If you write explicitly m psi bar psi, you will find it is psi bar left, psi right. Plus emission conjugate psi bar right, psi left. So you need left right. Okay. So to make the neutrino massless, you need to kill this term. So they decided to have, in fact, this was 90 something before constructing standard model. Salam, Landau, Glashula, it's very serious guy, believe that there is no right-handed neutrino because it is only left-handed because it is massless, and left-handed was already observed in the beta decay. Okay, so they constructed on this, and then it comes after that if it is weak interactions where the neutrino enters only with left-handed, and then forces a charged lepton to also enter the interaction with left-handed, then it's W, the gauge bosons that interact with left-handed only charged leptons and neutrino should also, this is like an assumption, but should also interact with the quarks in the same way, left-handed, because the similarity, as I said. Then they constructed a model in that sense. Okay?
ساعتها في physical explanation بس ان هم يفسروا الداتا
Which data?
اللي هي اللي مفيش رايت هاند
مفيش neutrino masses وانت ما تنفعش to write term in the Lagrangian give you large mass and so on.
بس ما كانش في physical explanation الليفت بس هو اللي له ماس.
No, this is a physical explanation.
مش موجود يعني.
لا, and construction could be started from avoiding problems, and then you take into account the assumption that you want to make left and right symmetric. You force that W boson is interacting in this way with the leptons, so Y should be interacting differently with the quark. So it's kind of logic more than that. Any students ask? Is new things, but already 2 lectures فيها دلوقتي, you can ask. At least if you don't understand something, please say. Okay, so now to have these symmetries, the nice symmetry SU2 cross SU3 cross U1, this symmetry exists, then the whole particle will be massless because it will forbid any mass term to the gauge boson or the fermions or whatever. You see from the Lagrangian air, there is no mass term for any particle. So the options is really try to break the symmetry softly or spontaneously or whatever, so that you generate mass to some particles. You know that the fermions should be massive, like top quark and all this down quarks and all this particle are massive, and also gauge bosons. Some of them are massive and some of them are massless. You know that the photon is massless. Gluons massless. And W, the gauge boson of the weak interaction, massive. Why it is should be massive? Why اشمعنى weak interaction W and we'll see also the Z should be massive? Simply because this is short range force, short range interactions. If the carrier, or what we call the gauge boson, is carrying the interaction is massless, then this will be long range force. Like the graviton should be massless because this is very long range force. Electromagnetic interaction is massless, and weak interaction is short range, and then it should be really massive. And also from, as I mentioned, beta decay that informed us in 1930s when we started to understand that there is some interactions called weak interaction from the beta decay. We estimated the mass of the W to be 80 GeV. So we need to construct now fundamental theory to describe the weak interaction, and the W mass is 0. So we need really to change this to make it similar to the prediction we obtained in beta decay. Yes? We agreed ان البارتكل اللي اسمه فوتون او دبليو او جلونز دول بنسميهم كارير، كويس؟ جيج كارير او فورس كارير. لما يكون عندك كارير خفيف هياخد الانتراكشن ويطير بسرعه الضوء، ده يعمل لك يعني الايفكت يبقى لونج رينج. لكن لو هو تقيل وخطه زي الدبليو اعمل الانتراكشن شوف. اوكي؟ نعم. ده كنت عايز استنى سؤال عنه. السترونج فورس او الجلونز ماسلس بس شورت رينج. ايه السبب؟ سبب مش ملوش علاقه، هو ماسلس بس ما كان نوت جو بياند النيوكلس. ده الاسباب تانية في حاجه اسمها لما تدرس السترونج انتراكشن كونفاينمنت وحاجات زي كده. لو انت انترستد نبقى ندسكاس ات ليتر. اوكي؟ بس هو ماسلس لاسباب اخرى يعني ريليتد ليه. عايز تقول حاجه سعيد؟ عايز تقول حاجه؟ لا انت كنت بتهرش بس. اوكي. وي جو اون اند يبقى اول معلومه اتفقنا عليها الستاندرد موديل اللي انتوا تعرفوه. لاجرانجر اللي انا كتبته بالنوتيشن بتاعتنا left handed only ما عنديش right handed neutrinos and all particles are massless and this is bad because في particles عايزينها تبقى massive. How to make this؟ مين السيمتري اللي هي يعني related للmassless W and weak interaction is SU2. يبقى انا محتاج to break the SU2. Okay, we started now to introduce, I think already Said introduced it, اللي هو symmetry breaking. عشان to break SU2 you need to get some particles أو some field charged under SU2. واتفقنا اللي charge under SU2 هو إيه؟ الدبلتنس، إن هو لازم يكون دبلت عشان أقول هو charged under SU2. كويس؟ ده charged under SU2 عشان دبلت يعني SU2 بتأثر عليه. SU2 كماتريكس الجنريتور بتاعها يأثر على الدبلت يديني نتيجة، فأنا أقول ده بيبقى belong to SU2. And also has hypercharge اللي هو U1 hypercharge اللي هو السيمتري الثالثة. So this means لو الهيجز فيلد ده أو السكيلر فيلد ده يعني break the symmetry هيبريك حاجتين، هيبريك ال SU2 and it will break the U1 hypercharge. And in fact we need to break the both عشان احنا عايزين الالكترومagnetism هو اللي يفضل remnant exact symmetry ويطلع لي الفوتون ماسلس مش الهايبر تشارج. الهايبر تشارج is يعني extended symmetry at higher scales هي مش الالكترومagnetism بالظبط. فده الهيجز فيلد اللي احنا هنستخدمه to break the SU2 cross U1. As a scalar field can be described by a Klein-Jordan equation, but this scalar field is charged under the gauge symmetry SU2, so the Klein-Jordan Lagrangian will not partial mu phi, you are familiar now. When we have gauge interaction, we have an interaction, we change the numerical derivative to covariant derivative. So the Lagrangian of the scalar will be d mu phi dagger d mu phi minus the potential d of phi, okay? And this is doublet, so the potential will be like phi dagger phi, like rho times the column, and to get some singlet, some number, and the lambda phi dagger phi squared, this is the simplest potential. And the idea now is really to take vacuum expectation value of this. What I mean by vacuum expectation value means the lowest energy state. In fact, this exercise before Higgs mechanism and Higgs was already studied for scalar field without gauge interaction. It's called the Goldstone boson. Did you mention? Okay, Goldstone boson. And if you have a scalar field like this, but no gauge interaction, so this is normal partial mu, and you studied the minima of the potential, you find either zero minima or non-zero minima, but there was a problem that you may studied in the last lecture, that there is massless scalar field remains in your outcomes, and this is contradict the nature that we observed no massless scalar field. So Higgs and his group take the mechanism and adjust it with the gauge field and they change everything to be gauge invariance. And then he studied exactly the similar way of the Goldstone boson, take the potential and study the minimization just to make partial V by partial the components of phi plus and phi zero, and be careful that Any non-zero vacuum expectation value should be for the neutral component, because this is an electromagnetic charge, because there is a hypercharging relation with electromagnetic charge. So you don't need to get any vacuum expectation value for phi plus, otherwise you will break the electromagnetic interactions and you generate mass to the photon. But phi 0 is safe. You can get vacuum expectation value, you break the symmetry of SU2, and you don't touch the electromagnetism. So this is what they did. You see here the vacuum V over square root 2. This is vacuum expectation value of phi 0. What's vacuum expectation value? This is, as I told you, the lowest energy eigenstates. So when you study the energy of, you see this is a potential energy, and the potential energy is given by the values of this vacuums of this particle. So this is the lowest value, which will give you some V to power 4 or something like that. Okay, so this is now 0 and V over square root 2, but this is, to have it, you need to have a very stringent assumption that the coefficient of phi dagger phi, which is supposed to be mass term of the phi field, should be negative, like I wrote it here, minus mu square. If you don't have this sign, which should be naturally any mass square to be positive, you will get the vacuum, this is identically 0. So no non-zero vacuum if the mass term square, mu square, is positive. You have to have mu square negative. And in fact, this was also kind of, ad hoc assumption to get non-zero vacuum. And then the explanation that this is not really the mass of the field, because this is just a bare parameter in the Lagrangian. And we will see that when we have this vacuum expectation value, we will do fluctuations around the vacuum, things will change, and the mass term of the scalar field remain physical, will have a positive mass. However, it was not very acceptable to start the Lagrangian with negative mu square. And in fact, one of the questions to go beyond the standard model to explain this type of potential, which, also the Higgs here, the scalar field, everything was in the standard model was built by gauge symmetry. Very nice. We have a gauge symmetry SU3, SU2 cross U1. And the construction naturally. Fermions will be doublet and triplet. Everything is fine. Suddenly we want to break. We don't have any ingredient to use it to break. Then insert some scalar field. What's scalar field? Higgs. What is Higgs? Higgs is a zero spin particles, which is not exist in all. Standard model was based on the particles that we observed already in nature. Then it started to be challenging. You are editing this by hand. Now it is no longer by hand because Higgs is discovered. You add potential by hand with negative mass square by hand to assume vacuum, non-zero vacuum in the phi 0 component by intention to get everything broken, and then you generate whatever you want. In fact, all this cooking give you very nice dish at the end of the day. So the vacuum expectation value with this V, you will find that it breaks the SU2. This is the isospin of the isospin of the SU2, and this is a hypercharge, and it doesn't break the electromagnetic charge, because the Q act on this vacuum expectation value give 0, and this means the electromagnetic remains exact. And this is really what we need. And this was not that obvious, by the way. Yes.
هل حضرتك مثلا الفريكونسي ده هي الكوانتيتي، الفريكونسي هي الكوانتيتي، احيانا بيبقى كومبلكس فبيدينا معنى جديد اللي هو الابسوربشن. هل ممكن الماس دي عشان هي كومبلكس معنى ذلك ان هي ماس بس لها معنى تاني؟
لا هي is taken not even complex, it is pure imaginary.
ان هي ماشي زي مثلا الفريكونسي ماشي معناه ان هو absorption.
I don't think ان احنا we need to look for any other meaning, because this is, as I said, it's trick, mathematical trick to get non-zero. People was not happy with this, But the response was, this is not the physical mass. This is just the mass term in the Lagrangian is pair. Will change to physical mass positive, and don't worry about this. However, we need to understand even the origin, the Lagrangian that we start with, the potential that we start with, how it looks, and why we have negative. So this is all this will take us to some other models.
احيانا التمبريتشر بيبقى موجب، دايما التمبريتشر موجب، بس احيانا في نيجاتيف تمبريتشر بيدي معنى جديد. ده انا قصدي كده يعني، هل ممكن يكون لها معنى بس؟
لا احنا we needed negative as a number عشان المينيمايزيشن بتاع البوتنشال يبقى نون زيرو. With explanation why it is negative is obtained in DSM. I will come to this point. Once you break, as I told you, you will have a nice result. The first important result is the W mass. You get it in terms of the vacuum expectation value of the Higgs times the gauge coupling. The interaction of the W with the Higgs in the covariant derivative I mentioned is related to the gauge coupling G2. And then it is obvious any particle interact with the Higgs with some coupling. This coupling will give the mass times the vacuum of the Higgs. So V squared G2 squared over 4, this is giving you the mass, very simple, very cute, small values, nice, V squared G2 squared, and this is the vacuum. And now we understand that if you need a mass, you have to interact with the Higgs. And also the mass is energy, is a vacuum energy. So in fact, this is related to the original proposal of Einstein of energy mass relation when he from classical perspectives, he said that energy equal mc square, energy and the mass, same things. And this is now really is not energy control. And in fact, in nuclear forces, we change masses to energy. Accelerator, we change energy to mass. We will see when we discuss the discovery of the Higgs. And now it's natural because the MW is given by V squared times some coupling. And once we know the mass of the W, we can also know the mass of the extra gauge boson related to SU2 because we have SU2. SU2 has a 3 generators. SU3 gauge coupling. The U1 hypercharge is another gauge field. So we have a 4. One of them is a photon, and then 3. 2 charged W plus W minus and the Z. And then the Z is predicted with this mass because we now know the vacuum from the mass of the W to be 80, and we discovered that the Z is 90 GeV. And not all of this, not all of this result, but we will get more result about the fermion masses. Fermion masses will be also related to the vacuum expectation value of the Higgs times the interaction coupling, the here gauge coupling, here the what we call Yukawa coupling. And then we understand for first time, you remember in the school when we try to define the mass, we don't have really a serious definition. It's, I don't know, أي شيء يجرى حيز من الفراغ ولا مش عارف إيه. But now we know the mass is related to the energy, and the energy is the lowest to vacuum energy. And the vacuum energy is an issue. We'll discuss it maybe in the gravity as well, because it may be source of the dark energy or cosmological constant or whatever. So this is really related to everything together.
So it was already discussed by Alex. Maybe you've discussed also the issue of the big divergence.
Hierarchy problem, yes. Yes. So the gauge boson W and Z is obtained in terms of the V squared, the vacuum, times the couplings of the interaction. The fermions is obtained by V times the coupling, which is Yukawa coupling. Higgs is interacting with itself. Then it is expecting to have a mass via the vacuum of the Higgs itself times the self-interacting coupling, and this is lambda. So the mass of the Higgs will be square root 2 lambda V because it is interacting with itself. And this was a very nice prediction to the standard model, especially MZ. MW, as I said, we fit the value of V to give you MW that we already know about it. So the real prediction was, first prediction was a mass of the Z to be 90 GeV. By the information of V, you get the mass of the Z. And then you predict the mass of the Z, and in Lab 2 in 1990 something, they discover, and then standard model becomes really acceptable. Moreover, the Z is neutral. And then we discovered that the weak interaction has another version of the beta decay, which is based on the charged current, that we have also neutral current. So you could have muon goes to neutrino, muon goes. So we have a neutral current mediated by the Z, and this was not known before, and this was also another discovery. No. Oh, sorry.
هو انا عندي confusion في حاجه وستك في السلايد اللي قبل اللي فاتت.
اللي قبل اللي فاتت ساكته ديت؟ لا تمام.
هو حضرتك بتقول ان الجرافيتون has to be massless عشان يexplain اللونج رينج بتاع الجرافيتي.
Yes.
which leads انه احنا بنقول ان الجرافيتي بتبروباجيت عشان according للجرافيتون moving. تمام؟ هو مش ده المفروض ان هو بيكونفليكت مع كون ان الجرافيتي bending في سبيس تايم؟
لا بص، هو الجرافيتي so far by graviton وكده ده type of quantum version of looking to the gravity which still يعني is not well established. الجرافيتي اللي احنا بنتعامل معاها classical gravity which is a kind of curvature in space time, but the curvature, the perturbation in the curvature is really what we call it the metric. The fluctuation of the metric is a gravity. The propagation of the curvatures is made by the, so it is connected, but still we are hoping to have a quantum gravity, and we're hoping to have a graviton, but no graviton is observed yet. The description that I am saying that the graviton will be carrying the gravity is kind of my dream, but not yet realistic. But I give it as an example of long-range force. If there is a graviton, and if the gravity is quantized in this sense, which is similar to the electromagnetic interaction, there will be photon and there will be graviton. Both will be long-range force. So keep gravity now classical. If you go from Newton to Einstein, this is great. Don't confuse yourself with much more. Okay. Any other? Here the discovery of the Higgs. I just need to mention you that all the theory, and in fact this things was not well accepted as any development in the physics. When we started to discuss atoms, at that time people was rejecting the proposal. And Higgs, for example, with Higgs mechanism minus mu square, Hawking himself was saying this is a mathematical trick and we will never get Higgs with lambda square root lambda V. However, we discovered, and in fact it was observed in 2012 at LHC, was 125. Remember the mass, the vacuum expectation value is 174. And in fact, 174 with a coupling, so we know that the coupling, to have a perturbative theory, the coupling should be less than or equal 1. In fact, the top quark, the largest top quark, the heaviest quark, we know that the coupling is order 1, and we expect the top to be 174. So we discovered the top to be say 174, and this was also success to Higgs mechanism before we discover the Higgs mass itself and the Higgs itself. But still we need to discover the Higgs to confirm the Higgs mechanism. Then we discovered, and the search was tough because lambda was unknown. Lambda is not gauge coupling, is not Yukawa coupling, it is self-interacting coupling. So people try to retake the coupling lambda in all the range, in all allowed range. From 0, if there is no interaction at all, it will be massless, and this is bad. This will be like Goldstone boson again. To 1, or even square root 2 pi or 4 pi or whatever. So the search was between few GV up to 700, 800 GV, to limited by the perturbativity. Lab 2, before the LHC, reached searches for the 100 something GV. and couldn't find any Higgs, and they make some bounds that the Higgs should be larger than 100 something, 114 or something like that. And then LHC came, started to look from hundreds up to 700, and you know, it was a very fortunate and very nice that after almost 1 year or 2 years from the LHC running, we obtained the Higgs, and not very heavy, 125, just above the limit of LEP2. So this was the case, and they discovered it in the process like H goes to gamma gamma or H goes to ZZ. Let me mention H goes to gamma gamma. I told you the Higgs is a chargeless. It has a zero electromagnetic charge. Because you remember, I take the phi 0, I make fluctuation around the vacuum of phi 0, so it is originally zero charge. So, but we know the photon is charged only, interact only with the charged particles. So how we can have H goes to gamma gamma? H is neutral. Gamma gamma is electromagnetic interaction, the photon. So the photon, usually you have E plus, E minus go to the photon, something like that. How to go to this? In fact, this is, I don't have the plot, but this goes via one loop where H goes to T bar, T plus, it's not T plus, T bar, and the T bar is closed. So you have one loop, and then T goes to photon, and the T bar from the other side goes to another photon. And this is what we call one loop correction. It's not at tree level, not H goes to gamma gamma directly, but go via some loop quantum field. I told you standard model is based on quantum field. To one loop, and then one loop goes to TT bar, gamma gamma. So this is really not only confirmed for us, is even kind of confirmation and success to the quantum field theory, because we don't have coupling from the beginning H to gamma gamma, but we have it via the loop if quantum field theory is really correct. Z, H to ZZ, this is the existing coupling. So HZZ and ZZ goes to 4 lepton, and also they discover the Higgs from this channel. You see the discovery here from this. So this is the standard model Z around G, around 19 GeV. And then the Higgs give you this peak around 125 GeV, and then this is the way the experimentalist Sharif can explain to you that when they have this peak, this is for invariant mass, will be indicating the resonance of this particle, which is indicating the existence of new particle. So this was a discovery of the Higgs at LHC, and confirming the story of the standard model, which started from 1930 with beta decay, then 50, then 60, and then Higgs mechanism and all this stuff, and we stayed from Higgs mechanism and Mr. Higgs proposal till 2012, about 60 years to discover Higgs. So for particle physics, 60 years is not that much. But now, after we discovered the Higgs in 2012, the 2013, where is Susie particle? 2014, where is the X dimension particle? Where is ground unification particle? Come on. Not every discovery is not every year. I have a table of the discovery in particle physics. You see the top quark, it takes even more than 60 years to observe. We should not relax and sleep and say, okay, when they have better energy, they will find everything. We need to work hard like our previous great scientists construct standard model very carefully and give all possible prediction, define the regions where people can really find the prediction. Anyway, let me now summarize the standard model, because I already
No, you have like half an hour.
good, because it's still evidence, I didn't go to the evidence. So standard model, I'm repeating science lecture. So standard model, to summarize, it's 4-dimensional quantum field theory. I am making this list to tell you later on how to go beyond the standard model. So standard model, when I say standard model, means quantum field in 4 dimensions. Invariant under Poincare symmetry, okay? Lorentz invariance. anyone will speak about violation of Lorentz or Poincare or whatever, tell him that you are beyond the standard model. A standard model is based on this gauge symmetry, SU3 cross SU2 cross U1. As I told you, if I have SU2 left cross SU2 right, this is beyond the standard model and this is different model. The particle content, fermions, Higgs, whatever, all of them are point particles. All of them are just single points. They have no dimensions. And this is the definition of the standard model, that it has particles with zero dimension, point particle. If you extend this to something else, and I will tell you that we really indeed extend it to one object, for one dimensional object, for example, this is a string, but this is not standard model, this is beyond standard model. We have a 3 fermions, quarks and lepton generation. Again, if you take much more, you are free to take much. Who said 3 generation? The 3 is a nice number, appears everywhere, but is not necessarily to the final number for the fermion generation. You can try 4 or more, but this is beyond the standard model, and you should be careful now that to make all the prediction of the standard model intact, and also to give other predictions that related to your extension. In a standard model, we discussed that there is no right-handed neutrino to keep the neutrino massless. Now neutrino massive, okay, I add some right-handed neutrino, okay, but this is beyond the standard model. This is not standard model anymore. Standard model, for some reason, just the economical reason, they based on 1 Higgs doublet. Why 1 Higgs doublet? Why not 3 like fermions and other I said 3 is nice number. So why not 2 Higgs doublet or 3 Higgs doublet? You can have, because there is no objection about more Higgs doublet, but you are taking yourself outside the frame of the standard model. Standard model has no gravity, as we said, so including gravity, this is required extension. Standard model, we will see that has no any candidate for stable particles, which we call it dark matter. So you search for dark matter, you didn't find, but we are keen to have candidates for the dark matter, and this candidates will come from model beyond the standard model. So this is the definition I told you about the standard model that we should remember, and we should be careful when I give you example of the extension that it will relax one of those assumptions. Yes?
Wouldn't violating the Poincare symmetry imply a violation of causality?
It will take you to a lot of things, yes.
Why?
But this is very restricted. It's not easy to violate Lorentz or Poincare.
Why would we even think about violating Poincare symmetry instead of trying, for example, to make the theory invariant under general diffeomorphisms?
Yes, but you should be open-minded. Some people come from time to time to violate things at some small limits in some very careful ways. Sometimes fake results said we are needing Lorentz violation and started to construct things. But here I just mentioned, if you wanted to do it, but you are outside the framework of the standard model. Now, evidence for physics beyond standard model. I will start with experimental evidence first to convince you that we really need to go beyond the standard model, and the standard model is not the final theory. Is a neutrino mass. I already discussed this. No right-handed neutrino, there is no mass, and then there is neutrino oscillation. Experiments now observed that neutrino oscillations exist, and the neutrino oscillation, to explain it, you have to have non-zero neutrino mass. And then started to think about extending standard model with right-handed neutrino, and the things is not that trivial. So you don't need just to think that, okay, standard model like this, let me throw a right-handed neutrino and then I'm fine. This standard model plus singlets called right-handed neutrino. In fact, you need to explain the mass of the neutrino, which is very tiny. It's 1 electron volt or few electron volt. So, and once you include you add right-handed neutrino, the mass will be okay. You will construct a mass term like lepton phi neutrino right that you add, but but now the Yukawa coupling should be 10 to minus 11 to give you the neutrino mass. And then they said no, but right-handed neutrino is singlet, pure singlets, is not invariant under SU3, is not is not charged under SU3, is not charged under SU2, is not charged under U1 hypercharge. So this is pure singlets, and then there is no any constraint on the right-handed neutrino mass. You can add it to the Lagrangian with heavy neutrino mass. And then they started to think that there is two mass terms, and then they construct the mass matrix and diagonalize. They get one heavy mass and one light mass, and then they explain the light mass with this seesaw mechanism, the seesaw مرجحة يعني. The heavy neutrino takes most of the mass, and the light neutrino will get very small mass.
هو ليه حضرتك لما تكتشفوا ان النيوترينو له اوسيليشن قال لازم يكون له ماس؟ ليه يعني؟
In quantum mechanics,
in general يعني.
in general, even حتى quarks, and if you don't have mass, you can diagonalize, and you can always make gauge eigenstates هي نفسها الماss eigenstates. There is no difference. But once you have the mass, the diagonalization is, then there is a mixing between the flavors. Oscillation means mixing. So that you know the oscillation, انت عندك you start with a 3 neutrino, neutrino 1, neutrino 2, neutrino 3, and then you construct electron neutrino, muon neutrino, tau neutrino. هل electron neutrino is just mu 1? هل muon neutrino is just, if there is no mass, I can do this. I can make the rotation such that flavor eigenstates, mass eigenstates, gauge eigenstates كلهم are identical. If there is a mass like the quark, في الحقيقة في الكوارك we start from up and down, up charm top down مش عارف string. we start حتى في اللاجرانجيان انت عارف we start with prime عشان بعد ما تعمل diagonalization you get the physical mass اللي هي pure down or pure up or whatever is still linear combination. اسمها angle Cabibo angle, for example, in the two generation, you have Cabibo angle. So you find that the down has a part of the original down plus something of the original strange. And therefore, you find the decay of the particle which has a down behave like strange, for example. So this is a mixing between the flavor or the gauge eigenstates. So the oscillation here exactly, in neutrino, we discovered the first oscillation comes from the solar. When we are expecting the electron neutrino to come in the earth with some percentage, we found there is a deficit, ولقينا تلت الكمية متحول لمليون نيوترينو. مفيش تفسير لده غير ان النيوترينو is a linear combination of the original eigenstates of the electron neutrino and the muon neutrino. This is what we call the oscillation. We call it a quark mixing. Yeah, for some reason the neutrino is called oscillation لأن الangles كبيرة و it makes really the transition between different states much frequent.
I'll just mention that before they discovered with Kamikanda and so on, the oscillations from one side of the Earth to the other, there was a big controversy about the solar neutrino model, and maybe there's something wrong with the model of the sun.
As usual.
Why are we, and then it was discovered that it was much more fundamental. Just for the
usual عندنا resistance to any new concept.
who had this model, who I knew a long time.
A lot of work is done to explain.
Banging on the table. Solar model is correct. You guys have a problem in the fundamental.
Okay, exactly like dark matter. What they are doing now in dark matter.
And
Here is dark matter.
Surprised and wasn't very happy.
Okay, so this is the second evidence that in standard model there is no at all any candidate to explain dark. Yes. انتوا الربع ساعة بتاعت الدسكشن احنا هناخدها خلاص عشان انتوا بتسألوا. This is better.
هو الماكسيمم ماس بتاع النيوترينو اللي هو محطوط هو مش حاجة ثابتة بس ليه ماكسيمم ماس؟ ده الحسب.
يعني ايه ماكسيمم ماس؟
يعني في كل الستاند او كل الحاجات اللي انا شفتها النيوترينوس
كام؟
ليهم ماس ماكسيمم يعني بيقولوا مثلا اقل من 0.1 حاجة بس مش حاجة محددة. الماكسيمم ده اتحسب ولا اكسبيرمنت؟
بص الحسابات ممكن نحسب لك الماس زي ما انت عايز. كبيره هنحسبها لك صغيره هنحسبها لك. هو المشكله الاكسبيرمنتال measurement للماس بتاعت النيوترينو is not that easy. They are getting us just the difference ما بين الماس سكوير بتاع M2 سكوير minus M1 سكوير M3 سكوير 3 و1 و2 و3 دوت جنريشن الفليفر الكترون نيون نيوترينو يعني ف3 تربيع ناقص مدينا ماس ديفرنس بتاع ماس سكوير. سلوت ماس لسه لم ترصد او تobserve yet. اكسبيرمنت ثيوريتيكالي زي ما بقول لك احنا يعني جاهزين بس ما ينفعش ندي ارقام كده كل واحد بالثيري بتاعته بيطلع رقم. اكسبيرمنتالي هي المحك في الاخر وكلنا بنحاول تبقى كونسيستنت مع المعلومه اللي جات لنا من الاكسبيرمنتس ان دلتا ام سكوير 1 2 او دلتا ام سكوير 2 3 less than 10 to minus 5 less than 10 to minus 6 كلنا نشتغل في الريجن. Dark matter is another long outstanding story problems from 1933 also, and now a lot of confirmation to confirm that not only the dark matter but about 95% of the matter in the universe is not observable, is not visible, and about 25 of them are dark matter and about 65 of them about dark energy. Dark matter or dark energy is beyond the scope of the standard model. Dark energy is an issue, keep it for a while. Dark matter should be normal matter, but it should be neutral and stable, and it has some interactions to give you the relic abundance, to give you the amount of the particle relics of the dark matter in the universe. The interaction, weak interaction, nice. So you need it to be weak interacting particles. You need to have a mass. You need to neutral charge and neutral color, and also you need it to be stable. In fact, we don't have in the standard model. The only neutral particle we have is the Higgs, but and it is massive and it's weak interacting, but it is not stable. It's fast decay. So it cannot play the role of the dark matter that is produced in the early universe and remains until now. This is what I mean by relic. Neutrinos. People thought that neutrino could be the dark matter because it is neutral, it is stable, it's nice. Stable means it doesn't decay to anything. But neutrino is very small mass, less than electron volt, and this cannot be explained the dark matter measurements so far.
Doctor?
Yes.
I have a question about dark matter. I already asked Dr. Said, but they too.
سيد قاعد خلي بالك ما تغلطيش.
Dr. Amr told me it's in the scope of beyond standard model. So I was asking.
هو ايه السؤال بس الأول؟
لسه هقول about the future collider.
Yes.
Okay. They are considering that long-lived particles. يعني هم عايزين يكتشفوا long-lived particles.
لا long-lived particle is not dark matter. ممكن يبقى long.
لسه هقول.
طيب.
Okay.
لا انت ممكن يكون عندك دارك ماتر ولونج ليفد بارتكل.
Okay, بس I've read that
Yeah.
they're assuming that long-lived particles could be good candidates for dark matter.
لا الا اذا كان very long lived particle يبقى عمر الويف الديكي ويدث بتاعه يبقى عمر الكون، وده مش لونج ليفد بقى، ده بقى يعني ستيبل اسينشال. فانا بقول لك لونج ليفد اللي بيدرسوه في الكولايدر مش فيوتشر بس في ال اتش سي كمان، ده اللي هو بيعيش نانو سكند مايكرو سكند، بحيث ان هو مش سكيب ذا ديتكتور. سكيب ذا ديتكتور مش عارف افرقه عن الدارك ماتر، ده هو تلاقيه كرييتد في النقطه ديت بتاعه البرودكشن، وبعدين في تراك اختفى، وبعدين هو عشان لونج ليفد ابتدى عند نقطه بعيده عنه، ممكن تبقى سنتيمترز او مايكرومترز او وات ايفر، بس في ديستانس ملحوظه ميسنج فيها التراك بتاع البارتكل، وفجاه ظهر انه بيتحلل. فهي ديت بيسموها ايه؟ ديسبليسد فيرتيسيز، نقطه البرودكشن مختلفه عن نقطه الديكي. فالبارتكل ده هو نيوترال وهو لونج ليف، لو هو تشارجد سهله ان احنا هنشوفه تريست كالتشارج، بس فجاه بيتحلل برضه فيها هي ديسبليسد فيرتيسيز، فده لونج ليف، ده ملوش دعوه بالدارك ماتر.
يعني we have detected some long-lived particles
لا.
from
We are making searches. مش انا اتش سي مش انا، لكن هم احنا بقى ايه؟ احنا بقى النظريات بتاعتنا تشوف فيها لونج ليف، فيها دارك ماتر. بصي نظريات طول ما فيش اكسبيرمنتال كونسترينت اونستلي نقدر نعمل لك بالفيزيكس
طب
شغل.
هما هيقفلوا ال HC فهيعملوا الكولايدر جديد.
ليه هيقفلوه بس كده؟ حرام عليك.
2030.
طيب في 2030 ان شاء الله يحصل ديسكفري. يعني اللونج ليف ده كانديديتس الدارك ماتر، في سيرش على الدارك ماتر بطرق مختلفه. يعني هو سكيب ذا ديتكتور ده حاجه، بس ممكن يبقى خارج مع بارتكلز وهو هرب فيبان في حاجه اسمها مونو بارتكلز. في كذا واي اوف سيرشنج فور دارك ماتر ات LHC. سيرش فور هيفي هيدز، سيرش. ففي سيرشز من هنا لغايه 2030 ده 4-5 سنين. انتوا يعني خلاص هتجيبوا ضرافه دلوقتي، اصبروا شويه. طيب دارك ماتر خلاص. دي مور ثيوريتيكال شويه، اللي هو فاكرين السيلف انتر اكتنج كابلنج لامدا اللي انا قلت لكم عليه، اللي هو عامل الماس بتاعه الهيجز. الماس بتاعه الهيجز دلوقتي از ديسكفرد. كام يا سيدي الماس بتاعه الهيجز؟ 125. اوكي، والفاكيوم از 174. تقدر to divide this over this to get the value of lambda. Lambda is at this, we call it, احنا we calculate it at the Higgs mass 125 GeV. قيمة the value of lambda is 0.12 or so. أعتقد 0.12. Fine. This is the value of lambda. Again, since we believe in quantum field and standard model based on quantum field, coupling is energy dependent. في حاجة اسمها renormalization group equation that takes the value of lambda from this energy scale to different energy scales. So someone is nice, but because we did this exercise for the gauge coupling alpha S, and alpha means the fine structure constant coupling square over 4 pi. So we have a gauge coupling of the strong interaction. So we have alpha S for strong interaction, alpha electroweak, and alpha electromagnetic. We did this exercise before, and we found that strong interaction, which is the strongest, بيقل مع الانرجي. الالكترومagnetic which is the weakest بيزيد مع الانرجي، وبعدين بيلتقوا. They meet at single point. This is what we call the gauge coupling unification, and we say, oh wow, there is a force unification and one force in high energy scale, and we are trying to unify all the forces in one from this exercise. When we studied the energy evolution of the gauge coupling, so they did the energy evolution of the lambda, which started from 0.1. We know it is weak interacting as a coupling of the Higgs field, and we know the all possible terms in the RG, and then you run. Then there is a surprise that at some scale less than 10 to 10, the coupling cuts the zero value and starts to go to negative value. Then this is a problem, because this coupling originally is a self-interacting coupling which we assume to be positive. Lambda phi to power 4 theory has to have lambda larger than 0. So how it becomes negative? And this means in the early universe, which has energy even higher than 10 to minus 10, you start with unstable potential. So this cannot be the case. So they try to change the couplings, the mass of the top, the alpha S. They found that for natural values, really it goes to negative values. And this was an issue to make the Higgs potential that we are using is unstable. And then we discovered that this is required even second Higgs or 2 Higgs doublets or some extension of standard model. It will be easily raise up the curve of the evolution of lambda to make it all way positive. So this is taken as an indication of physics beyond the standard. We need further interaction to interact in particular with the Higgs. Can please?
هو ازاي الجود كانديديت للدارك ماتر يبقى ستيبل وفي نفس الوقت يفول ويك انتراكشن؟
سؤال كويس. الانتراكشن in the annihilation هو stable particle. هو بيسموه مايورانا بارتكلز، يعني هو نفسه الانتي بارتكل بتاعه، الايكوال انتي بارتكل. لو عندي دارك ماتر في انتي انت عارفه زي النيوترينو، الانتي نيوترينو، الكوارك انتي كوارك، حيث ان هو نيوترال في كل حاجه، فهو از ايكوال تو ذا انتي بارتكل بتاعه. المهم يعني دارك ماتر when they meet they annihilate. هو it doesn't decay لكن it can annihilate. عشان كده in the early universe لما بنتكلم على الريليك abundance بتاعه we start with huge quantity of the dark matter in the universe because after Big Bang كل المطر has produced, and then the dark matter meet each other. They started to annihilate and to produce standard model particles. And the temperature is high, so the standard model particles are annihilate or are producing the dark matter again. So dark matter goes to quark, anti-quark. Quark, anti-quark goes to dark matter. As the energy is high and large, this process goes and back in two ways. We said the particles in thermal equilibrium until the temperature go down of the universe. The universe is expand and temperature is reduced. Once it is reduced, dark matter meets some dark matter, it annihilates to quark, anti-quark. But quark, anti-quark has no temperature, has no energy to reproduce the dark matter. Then it remains quark, anti-quark, and dark matter is reducing the number. And so on until the dark matter cannot find another dark matter to annihilate, and this is what we call freeze out temperature. And ده اللحظة اللي dark matter remains stable and remnant until now. فاحنا we need annihilation and عشان to keep the relic abundance exactly as we want, you need very careful annihilation. It cannot be annihilated with very strong coupling, otherwise it goes away all of the dark matter. It cannot be very weak, cannot be gravitational, for example, otherwise you will annihilate very little and the universe will be closed by dark matter. You need very specific, and we found this specific coupling could be of order the weak interaction. For that reason, we believe the dark matter should have kind of weak interaction.
يعني احنا مهمين بالبيك انتراكشن ان الماتر نفسها عندها انيليشن at some conditions معينه مش ان هي عندها short range لايف تايم مثلا.
No. If it is weak interacting ممكن تبقى annihilated via Z او ده مش ممكن يبقى تشارج via Z. يعني انا dark matter ممكن يبقى معاه interaction مع Z والZ goes to P plus minus مثلا. فالفكره كلها ان هو it has an interactions مع الويك Z او interact مع الهيجز مثلا with a Higgs coupling of the weak interaction. ده عشان تظبط الانهيليشن وتجيب يو ذا ريليك اللي احنا عايزينه.
Generically with the radiation method.
نعم؟
Generically with the radiation method.
which radiation؟
Radiation.
مين اللي
Thermal method.
اللي هو to go out اللي هو dark matter annihilate to some radiation.
Yes.
ما هو quark anti-quark منه massless. It's massless at this level, that's called radiation.
But it could be other things.
Yeah, all stuff. Another example is called the hierarchy problem. Again, quantum field of the standard model maybe is good, but creating some problems like the running of lambda. Also the one loop correction of the Higgs. If somebody studied quantum field theory, finds this loop correction, we call self-mass interactions or self-mass corrections for the electron. So the electron has this one loop correction, and the mass of the electron is not just the m0 that we do it in the Lagrangian, but m0 plus the correction from the one loop. And since the one loop is small, two loops is smaller and so on, so perturbatively we can use one or two loops on. Nice, very good correction to the electron mass. So the electron mass have delta ME coming from this. This loop usually, when you study quantum field theory again, has a problem. It's called divergence. We parameterize with some cutoff lambda, which is the highest scale you have. But nicely that this lambda comes from this correction as a log lambda. So lambda, even if you take it very, very high scale, gut scales, 10 to 19 GeV scale, the log will give you just as a factor 19 times ME times a factor 1/100. So this is give you something of order 0.2 correction of the original mass. So you start with the electron mass, ME, you don't know exactly what it is. You add the one loop, which is giving you 0.2 2 ME, and then you said this is should be physical equal to the physical mass. Then the two one large value plus a small correction give you the array. Let us do the same for the Higgs. The loop correction for the Higgs, which is a scalar, I told you they added by hand as a first scalar field, and this was the issue, discovery of the Higgs, not just completing the standard model, but also absorbing the first scalar particles. Scalar particle is different from the fermionic particle because it has a corrections like this, and this correction now, in fact, also it's related to the divergence lambda, but not only log lambda, but even lambda square. It's called the quadratic divergence. So can you imagine I start with MH in the Lagrangian, I want it to be of order 125 GeV. I got the correction of delta MH of order lambda square. If you take lambda square 10 to 16, 10 to 19, or gut scale 10 to 16, you get very large correction. You get the delta MH square of order delta MH square 10 to 30, delta MH 110 to 15. You needed 125. You take M naught, and the one loop is 115. You need to take M naught to be 115 plus minus 100, which it's impossible. It's very fine tuning. So this was a problem in the standard model. Theoretical problems about the quantum field theory of the scalar field and the correction of the mass of the scalar field, and how we can really protect the electroweak physics and the Higgs mass from the high scale correction and the blank scale physics. And this cannot be done in the standard model, and we need to be on some. Another evidence, I go quickly flashing this, something is called baryon asymmetry, why we have a matter and we don't have antimatter. Matter and antimatter supposed to be produced in the early universe in equal amounts, but due to some baryon number violation, CP violation, and so on, you can have some mechanism to annihilate the antimatter and to keep the matter. However, standard model, we agreed that this is nice proposal by Sakharov since 67. However, standard model cannot account for all this. It gives us some small violations, matter antimatter violation, and it cannot explain this current observation for baryon minus anti-baryon, which is order 10 to minus 10. Other questions that we are trying to understand better to understand our standard model. Why three families only? Why electroweak is broken by this minus mu square? Why this symmetry SU3 cross SU2 cross U1? Why not simple group SU5 or SO10, which contains all these groups, and then better unification, not just partial unification? And where is gravity? Why the masses is taking this value for quarks and leptons? We understand masses now is given by the vacuum expectation value times the Yukawa couplings. But again, we change the question: why the masses with these values to why the Yukawa coupling takes these values? So still the problem of the flavor issues remains, and this is related to the thermal masses. Cosmological constant and dark energy as an issue. All this question has no clue at the standard model. Maybe last slide, the directions beyond the standard model, or possible direction beyond the standard model. As I told you, you get the list of the definitions that I mentioned. Relax each one, you get new extension. So the gauge symmetry, if you change SU3 cross SU2 to another symmetry, gut symmetry SU5, SO10, if you add U1 P minus L to explain the neutrino masses, if you add SU2 left cross SU2 right to explain the left-right symmetry, all this is taking you to beyond the standard model. This class of physics beyond the standard model is called based on the gauge extension. You can also extend the Higgs sector. As I told you, there is no reason to say one Higgs sector, one Higgs duplex. In fact, most of the models, gauge sector or other sectors that I will discuss, always give me Higgs with more than one Higgs duplex. You can extend the matter sector. You can add right-handed neutrino. You can add vector-like fermions. You can add extra matters. This is another way to extend the standard model by extending the matter sector. The flavor, as I told you, the masses, the hierarchy, you need to explain the flavor, and there is a lot of work to understand why the masses take these values, because will take us deeper to understand the symmetries, and in particular new symmetries, not only gauge symmetry and the space-time symmetry, but also we could have a flavor symmetry. The extra dimensions. Why 4 dimension? We could have extra dimension. Extra dimension, it looks like we are talking about something related to gravity. This is true, but it has also impact in the particle physics. And in fact, no impact. Keep it to the next page. So we have now, after extra dimension was proposed long time ago, some models to revisit the extra dimension, like this Randall syndrome, Arkan Hamidi, D modulus D valley, ADD. They are interesting. They have interesting and nice proposals. So this is also kind of extending standard model by extending the space-time itself. Supersymmetry. This is another. It was, and I hope it remains, one of the popular extension of the standard model, because it extended the symmetry of the standard model to keep fermion and the boson, and this is natural. Why we have fermion and we have boson? Spin 0, spin 1, spin half. So they relate fermion and the boson by a symmetry. This is also like an extension of Einstein theory of special relativity by extending the Poincare symmetry to something called super Poincare. So it has a mathematical origin. Extending space-time includes the fermion-boson symmetry, and this has helped a lot in stabilizing the Higgs, solving the hierarchy problem, and predicting several things. In fact, it predicted the Higgs mass to be less than 130 GeV, and the Higgs discovered to be 125. So you imagine if it is 135, supersymmetry will be gone. But fortunately, it was nice, and it seems correct prediction. So still there is a hope that LHC or future collider can tell us supersymmetry exists or not, because it will be petty if the nature is not including supersymmetry. Supergravity, if you include gravity to the standard model, in fact you can include gravity, general relativity, gravity, cross product, that's it. But in LHC and in collider, we neglect gravity. When we go to black holes and early universe, maybe we include other interactions, electromagnetism and weak and strong, to discuss these things. But we need something even more than just the cross product of gravity. And okay, we need to quantize gravity to be able to do this, but also even without quantization, even classical gravity can be included naturally. If you take supersymmetry, remember I told you we have SU3, SU2, this is gauge symmetry. It's, I'm sure you studied in the beginning, it was global symmetry, and once you make it gauge, you started to introduce a gauge field and you make the theory interacting. Here we are, supersymmetry could be global symmetry. Once you wanted to change global supersymmetry to local supersymmetry, you find that the gravity enters the game and you get supergravity. So for first time, gravity is not added by hand or cross product to the other interaction. It comes naturally when you have supersymmetry as a global symmetry and make it local, get supergravity. And then it gives you supergravity in different versions, not just as a supergravity that we know about Einstein gravity, but more involved gravity and more interesting, and this is nice things. Superstrength. Once you change point particles, that I told you, the electron is point particle, top quark 174 point particle, Higgs 125 point, all particles point particle. If you extend the particles to be one-dimensional object, then you are in different theory. This is called the string theory. Then you have one-dimensional object, it's called the string, and the vibration of the strings is giving you different modes. Different modes means different particles, and this is very interesting idea because it's unify all particles, not only boson and fermions. All fermions, all quarks, everything comes from one string and is giving you different particle based on different oscillation or vibration. But of course, outstanding proposal means outstanding proof, outstanding time. So still the theory is under construction, is not yet final. But again, we should be like we are patient with the collider and with the experimental measurements. We have also to be patient with the construction, because sometimes theories needs time to construct. Especially string theory, it works mainly at high scale, and then the experimental verification and the predictions will be rare. So, but anyway, make it first mathematical consistent, complete your theory, and then we discuss how to verify it. So that's all for the first lecture. Next lecture afternoon, we will discuss, as I promised, one example. I will keep the example surprise for you, which extension I will use it from the list. Okay? Thank you very much. خلصتوا أسئلتكم.